starting our presentation, I would like to ask you guys a question. Does anyone of you know what is the current record for the highest speed achieved by a train? The highest speed achieved by a train, in railways. Speed. Yeah, Nessa.
Something around 600 kilometers per hour.
Can you tell which country, which country?
Japan.
Yes, correct. Very smart, Nessa. Well, the technology that they use to achieve this high speed is known as maglev technology, and which is what we will be presenting on, is maglev technology used in transportation. Now, first question is, what is the need for such technology, like an alternate form of travel? Now, firstly, these are the existing forms of technology that are used in mass transit public for long distance travel. First is the railways and the aircrafts. Now, these technologies in their current form are already on the top of the technology curve, and the innovations that take place in their performance to improve their performance are only very minor. So, and on the other hand, like we are moving towards a globalized world, there is more and more need for long distance travel and to do it in a shorter time. So in future, we believe that these current forms of technology will not be able to meet this need. So, and the second point is that these forms of technology also cause a lot of pollution, they harm the environment and are energy inefficient. Trains take a lot of energy and they give very little performance. And aircrafts also use engines that run on fossil fuels. So therefore, we need an alternate form of technology, which we believe would be this maglev technology used in trains. Now, maglev is a short form for magnetic levitation. Now, for those of you who don't know the meaning of the word levitation, it actually means being suspended in mid-air, like floating in mid-air, as in defiance of gravity. Now, this is what actually maglev does. The tracks, which are known as guideways, the train does not actually touch these tracks, it actually floats on top of it. So as a result, there is no friction. So this allows it to achieve very high speeds. The only friction, the only reduction in speed is caused due to the air resistance it faces when it moves forward. Now even that is being overcome. There's a company known as Swiss Rapid, which is building tunnels, which would be partially vacuumized, and trains would then overcome this air friction as well. So if this technology is developed, this current record of approximately 600 kilometers per hour would be broken pretty substantially. But we won't be discussing this. This is the technology of the future, and we would be only focusing on the current form of this technology. And the last point is that since it runs on magnets, there is no form of emission. So as a result, there is no pollution also in this technology. Now, before I proceed with this slide, I would just like you to recall some of grade 9 physics. Now, we had learned of a phenomenon known as electromagnetism. Now, that basically is that when you pass electricity through a metallic object, it temporarily acquires magnetic properties. And the other is that a magnet, it consists of two poles, a north pole and a south pole. And when you bring two like poles together, they tend to repel each other. And when you bring two unlike poles together, they tend to attract and join together. So the first form of technology that maglev uses is called electromagnetic suspension. And this makes use of electromagnets and the principle that two unlike poles attract each other. In this, the guideway has, it's made of steel. So when you pass electricity through it, one end of this guideway attracts the train from above, the other attracts it from below, causing it to be suspended in mid-air. The other makes use of the complete opposite principle that like poles repel each other. So basically in this technology, which is known as electrodynamic suspension or EDS, the guideway acts as a magnet of one pole and the train acts as a magnet with a similar pole. And this repulsion force between them causes it to be suspended in mid-air. The actual function is much more complex, and I will not be going into all that. The basic basic point I'm trying to make is that two different technologies having different principles are being developed simultaneously. Well, the first one is being developed by Transrapid International, and it's a German company. And the recent Shanghai maglev train, it was developed by Transrapid, and I think it started operations now must be in 2004. 2004. So basically, that train that runs there makes use of EMS. And the other, the train which achieved the high-speed record of 581 kilometers per hour, was developed by JR Maglev, which is Japan Railways maglev systems, and it was achieved using the technology known as electrodynamic suspension. So that's that for theory. Now, I'd just like to make a quick note on who the stakeholders are in this technology. First are the developers, that is the firms like JR Maglev Systems and Transrapid, and the engineers and scientists who are developing this technology. The second are the government and the countries, that is the people who will be adopting this technology. And lastly, the public at large, whom this technology will ultimately benefit. And on this, I would also like to make a note that in our presentation, we would be presenting from the point of view of the maglev technology industry as a whole, and not from the point of view of a particular company, because this is a public good and the beneficiaries would be the public at large. On this note, I would like to hand over the presentation to Mr. Sandeep.
Thank you very much. Any questions?
What's the visibility of this technology in the Asian market? This maglev technology.
There is a lot of demand for this technology, but like right now, since like Asian markets are the ones who are developing this technology most, the early adopters of this technology are South Korea, Japan, and China. So these are all Asian markets which are developing further, and even the German developers and the European developers and the developers from US are actually coming to countries like India to like promote their technology, because it does not have much appeal in their countries.
Really, it's great technology, but is there any scope of economy of scale if large scale adoption is made? Will it have any economy of scale if very large scale adoption is made?
There will be learning effects, definitely. As you can see that when the Shanghai maglev train was developed, and when the Japan, it cost $1.2 billion. When the Japan train was developed, it cost around 100 million per kilometer. But now they are like estimating their next plan, Japan's next plan is supposed to cost like 18 million per kilometer, which is a drastic reduction. So
it's decreasing some kind of.
Yeah, so that is why, yes, there is some.
This is a technology adopted in a sky train or in a high-speed train, like only in the cities and cities or just in the city.
Right now, it's being implemented intra-city. The projects that are like currently operational are intra-city, but the main plan, the main market is for intercity travel, as we had said, for international travelers. That's the main market, which they have not tapped yet, but they are plans. Right now, it's intra-city, like within city, like connection between the airport and the railway, or connection between the airport and certain stations.
Okay, do you think this technology can substitute the normal train?
Oh, I'm sure that it will.
So what is the prediction? Like the prediction by themselves, like what is it actually?
We didn't want to give the exact figures for the S-curve, but around, it will start diffusion, it will start the acceleration.
How many years will it actually take the technology to get actually developed?
We believe that it will take the accelerating phase by around 2045 when intercity travel starts.
2045.
2045 when the actual train from Japan, intercity train in Japan is implemented.
Okay, so any question? Yeah, okay, thank you very much.